Hello fellow problem solvers. So today we're doing a problem from the Indian IMO Training Camp, day 4, problem number 1 from 2019. I suggest you try this nice number theory problem out for a minimum of 25 minutes, half an hour. Ideally, hour to 2 hours, not more than 4.5 hours if you'd like to go along with us. Put your first ideas out on paper for the next 5 to 10 minutes. And now let's begin. So, okay, this seems like a fairly simple formulation. F of n divides f of 2 to the n minus 2 to the power of f of n for some polynomial f, a monic polynomial. A monic polynomial means it's just like f of n is f, let's do f of x is going to equal to x to some power, say k, and monic means that it's like x to the power of k is the leading term. The leading term is multiplied by 1. And then plus a1 to the power of x to k minus 1, all the way till an. And these other ai's can be any integers. They can all be 0, they can be minus 1, plus 1, any up to 2,000, minus a million, and so on and so forth. So starting from sum m, we have this is true. Okay, so what are we going to do here now? Using polynomials, when we're working polynomials in the integers, it makes sense to try to see if we can use this fact in some way, shape, or form. It's generally used somehow. Sometimes you just need a smart application of this to get to something useful, maybe a solution perhaps. Here that seems a bit difficult because we really don't have this. We have 2 to the f of n. So this is going to be a bit more difficult to use directly. We might need to get at it indirectly. So one thing to think about then is, okay, this f of n, it's hard to maybe work with that specifically. Like it might get clunky or complicated, but let's look at prime factors of f of n and what happens with a prime factor divides f of n. What can we say about these two f's of these two things? Here I invite you to pause for the next 10 minutes, pause the problem further. And now the next idea is, okay, let me try to use this fact in some way, shape, or form. I want to have a minus b be equal to p. Okay, let's say I have 2 to the n to get to this, and I'll need 2 to the n plus p for a, and I have this situation. This is going to then divide f of 2 to the n plus p minus f of 2 to the n. Again, this is all fine and nice, but it doesn't really give me this. Though maybe I can get to this indirectly, maybe using the fact that p divides f of n. So then let's write p is equal to, I'm going to have some n plus k minus, actually not n plus k, n plus p minus n will give me then f of n plus p minus f of n, and then I'll get what I need. Then I'll get that p divides f of n plus p, and then maybe this divides f of 2 to the n plus p. Maybe there's something I can work with there, and actually that's a good thing to maybe look at. But also we can generalize this as to p times t, p times t, p times t, and see a more maybe general way of looking at what's happening. So let's start first off with the simple dt equals 1 case. What do we have? We have from p divides f of n, we're going to get that p divides f of n plus p, and we know this thing divides f of 2 to the n plus p minus 2 to the f of n plus p. Okay, now how can we, what is this equal to? Like what is this maybe congruence to modulo p? Think about this. Pause for the next 5-10 minutes and think about it. How can you get this to something closer to 2 to the n? Okay? And here's the next idea. Well, what I can do, I'm looking at f of 2 to the n plus p modulo p. Okay? What I'm really what is this equal to? There's a couple of ways we can go about this. One way is to say, okay, need to look at modulo of p. So I'm going to need p divides this minus something smaller than that. Now what will I do here? Well, let me see if I can make something similar that I had before. So I'll need to have 2 to the n plus p, and maybe a p that divides this. What do I use? Well, p divides 2 to the p minus 1 minus 1. So if I want to get n plus p, I'll multiply this by n plus 1. And then I have this divides. So this is n plus p minus 2 to the n plus 1. Then I get this thing divides this, f of 2 to the n plus p minus f of 2 to the n plus 1. So this f of 2 to the n plus p is congruent to f of 2 to the n plus 1. So from here, I actually get this thing right here, right? From this, I got to this, just by using congruency modulo p. Now, what can I do with this? Well, now I'm looking at powers, right? I'm trying to see 2 to the x, and what is that modulo p? So what do I need to look at? Well, modulo p minus 1. So I need p minus 1 to divide f of n plus p minus some f of something else. So I need to have n plus p minus 1 to get p minus 1. Well, minus n plus 1 is going to give me p minus 1 divides f of n plus p minus f of n plus 1, which means these two things are congruent to modulo p minus 1, which means 2 to that thing, n plus p, minus 2 to the f of n plus 1 is divisible by p, because the order of p, or the period of 2 to the x modulo p, is definitely going to be p minus 1, or a divisor of p minus 1. So with this in mind, we now have from here f of n, actually not f of n plus p, but f of p. P divides f of 2 to the n plus 1 minus 2 to the f of n plus 1. So from p divides 2 to the f of 2 to the n minus 2 to the f of n, we have it divides 2 to the n plus 1 as well. And here, actually no, from p divides f of n, we have this. And now from here, I invite you to pause for 5 minutes and generalize this to, instead of just times 1, like n plus p, do it n plus p times k, and see what do we have for something general. Pause for 10 minutes and try to do that. Now let's clear up the board and do it. And we get this thing right here. So, like just doing these steps, the analogous steps that we did for case equal 1, we generalize it and we get this divisibility relationship. Now, with this, can we do anything more now? What were we doing back here? We were really just, for one of these things, like we were really just subtracting this number modulo p minus 1. We were just subtracting p minus 1 many, many times. So we could do the same thing to both of these again, and we would get that p divides whatever this thing is modulo p minus 1. Because, for example, let's say that this prime, so let's say that n plus k is congruent to r modulo p minus 1. Okay? Then we know, what do we do here? We did, actually here we did 2 to the n plus k minus 2 to the r divides this. It divides f of 2 to the n plus k minus f of 2 to the r. And this thing right here is 2 to the p minus 1 times some constant, some c, minus 1 times 2 to the r. Okay? And that is because this minus this is divisible by p minus 1. And now that's how we'll get f of 2 to the r, that p divides f of 2 to the r minus this. On the other hand, we'll get the same thing we got here, p minus 1 times k, we get p minus 1 times c is equal to n plus k minus r. And from there we get this thing divides f of, what's it called, n plus pk, so here's of n plus k minus f of r. And so we get that 2 to the power of this is congruent to 2 to the power of this modulo p. So if we look at any r, any remainder modulo p minus 1, we can get that p divides f of 2 to the r minus 2 to the f of r. And mind you, this is for any prime. So we've got that for any prime that divides one of these numbers, we'll get that it divides all the possible remainders modulo that prime. Now, here I invite you to pause for the next 20 minutes to try to push the problem further. What's the next idea? How are you going to do it? And let me clear up the board now. So what we've gotten to is for every p that divides f of n, we have that prime p divides this for every single r. For every r that's less than or equal to p minus 1. Now, not just less than or equal to p minus 1, but actually every single r that's in the non-negative integers. Now this sounds like, mind you, what's the solution to this? What do you think is it? What is your intuition telling you? My intuition here tells me that f of x equals x is a solution. So this thing right here makes sense. It makes sense that this would be 0 always. Like maybe there's other solutions, but I can't really see them. Maybe, okay, it says non-constant polynomials, so a constant. Maybe could a constant be a solution? No, I don't know actually. But actually maybe a constant could. F of n be a constant. A constant would divide. Okay, maybe a constant power of 2 would also be a solution. But we're not looking at those. Like it seems this is strongly favoring for me that the solution is f of x equals x. Or maybe there's others. Now, what we've done so far is played with some modular arithmetic, and we got one prime number. And we've used the fact that it was a prime by looking at its, really, the periodicity is p minus 1. The period actually is p minus 1, definitely. And we've used that fact. Now let's see if there's something else we can do here. And maybe if we had, now we have one prime that divides this. And we can maybe fix this to be 0, 1, 2, whatever fixed number. And if we can get a lot of primes, then we can prove that these two things are in fact, that this is equal to this. Right? If we can get a prime as large as we want to get it. Now, how would we get such a prime? We need to have this prime p divide n. We need to have arbitrarily large primes that divide f of n. Can we get that? Pause for 5-10 minutes and try to see if we could. And the answer is, well, that is to say that the prime divisors of f of n are infinite, right? That is what we need to prove. Well, let's assume they're finite. Let's see, the primes that divide at least one of these are p1 through pk. And now if we take, say, f of x is x to the n plus a1 x to the n minus 1, plus all the way till an, how could we get a number here that is not divisible by any single one of these primes? Right? Well, the answer is, okay, I want to get everything out. I want to get an first out, so I'll take x that's divisible by an, and then I'll have an outside, so I'll get a plus 1 here, and then I can just get internally everything else to be divisible by all of these primes. So if I get an times p1, p2 to pk, f of this is then going to be divisible by none of these primes. Because if a prime, say pi, divided this, say some pi divides this, then we would have pi divides obviously every single one of these x's. So it needs to divide an. Okay? So maybe there's now how do we maybe fix this or do we actually need to fix this? Like, it doesn't actually mean that we have to have every pi not divide this, but mean that there needs to be some other prime number that's a divisor of this. So let's look at what this actually looks like. This is an, take it outside, and then we get an to the power of n minus 1. Let's call this product p to the n, plus a1 times p to the n minus 1, and then an to the power of n minus 2, plus all the way till a to the n minus 1 times p, and we're also now going to have times an plus 1. Now, is every single one of these, is this number divisible by any of the pi? And the answer is no. Because if pi divided this thing right here, then we'd have pi needs to divide 1. And that would be a contradiction. So, just by virtue of this, we have that there are infinitely many primes that divide f of n, starting from any n. And now, given that, what do we have? We have infinitely many primes exist such that p divide this. So if we fix an r, say, fix an r, then take a prime number that divides some n, divide some f of n for n greater than or equal to m. If there are infinitely many prime numbers that divide this, we can pick a p such that this is true and that p is greater than the absolute value of the difference of 2 to the f of r minus f of 2 to the r. I switched this around, but it doesn't matter. And then if p is greater than this, we'd get from p divides f of n, and we can actually pick a p that's greater than anything because there's infinitely many primes. You can pick n. If you have infinitely many primes, you can pick them as large as you want because primes differ by at least 1, right? So that's why you can pick this. You can't always say if my set has an infinite number of elements, I can pick as large an element as I want, right? The set 2 minus 1 over 2 to the n for n1 for infinity has infinitely many elements, but you can't pick the largest one. But you can't pick one that's as large as you want it to be. Like there's no element larger than 3. So that's the thing on the integers that you can usually do that. So we have a p such as this, and then we get that p divides this difference, from which it follows, because p is greater than their absolute value of the difference, that follows that this difference is in fact equal to 0. And so for every r, we have 2 to the f of r is equal to f of 2 to the r. Now pause for 2 minutes and look at what is it that we have just proved. Well, we proved this is the case for all r that are greater than or equal to 0 and, that are in the non-negative integers, right? This is what we have proved. What's our problem condition? This divides this. We've just proved that this expression right here is always 0. So that means we have used the problem condition as much as we could have used. Like we can forget about it now and just focus on this thing being true for every single r greater than or equal to 0 and a non-negative integer. Right? So now we can forget about this completely and just focus on this. And from here, because mind you, if this is true, then this is always true. Right? So then the problem condition holds. But if this is true, we've gotten then this one needs to be true. Which means what? We can focus on finding an f, a monopolynomial, which satisfies this relationship. And here, I invite you to pause for the next 5 to 10 minutes and ask yourself, what are you going to do now? How are you going to proceed? Try out a couple of stuff. And now here's the next sort of idea. So, we have this thing right here, which is our new problem. Find all f such that all f monopolynomials such that this is true. Okay, let's get back to our basics. A minus b divides f of a minus f of b. Can we use this fact here in any way, shape, or form? Like, what would be sort of a thing you would try out first? For me, let me see if I can get, f of 0 is 0. So, plugging in b is 0, I'll get that a divides f of a minus f of 0. Okay, can I plug something in that makes this look nice to me? That gives me something nice here. Pause for 5 minutes and think about it. And here's the big idea. Let me use this idea right here. So let me set a to be equal to 2 to the r, and then I'll have 2 to the r divides f of 2 to the r is equal to 2 to the f of r minus f of 0. Right? I'm using this immediately here. And now what do I have from this? Well, the answer is, okay, this is the power of, like, a huge power of 2 divides this difference. F is a monic polynomial, which means also its graph. This is a very, very cool problem, by the way. Like, I'm just enjoying it as I'm solving it with you. So its graph is going to look like something like yada yada, but it goes up to infinity at some point. I mean, it can be a linear polynomial. If it's monic and a linear polynomial, it looks, something like this. Like it's a line that you either add 1 or subtract 1. Add some constant or subtract some constant, from someplace. Now, this is how our polynomial looks like. So, unless, if it's a linear combination, we might need to look at some things. But generally speaking, we should be able to get this f of r to be as big as we want. And even if it's linear, we can get this to be r minus some constant, right? Which in turn means that we will be able to get this thing, maybe this is divided by some 2 to the r minus some d. We'll definitely be able to take an r such that f of r is greater than r minus d for some constant d. Right? Such a constant definitely exists in our polynomial. And what would this constant have to be? I just need to think about that for a second. Like, the only question is, like, if we have a linear polynomial, we would have to have this d be bigger than the absolute value of a0 of f of 0. And I think that's about it. But we can definitely choose such a d, because this polynomial, as n increases, f of n grows much bigger. So we'll be able to pick an r such that this is true, which means r minus d, 2 to the r minus d, will divide this, which means 2 to the r minus d will divide f of 0. And this is for an arbitrarily large r. Which means what? It means that f of 0 is going to have infinitely many powers of 2 that divide it. And so f of 0 needs to be equal to 0. Now, we've proved now that f of 0 is 0. Now what do we do? What's the next step? Pause for 5 minutes and figure it out. And the answer is okay. Now if I plug in r equals 0, I'll get here f of 0 is 0. I get 2 to the 0 is equal to f of 2 to the 0, which is f of 1. So f of 1 is equal to 1. And now what do I plug in next? I plug in r equals 1. And I get 2 to the first is equal to f of 2 to the first. Now or f of 2 is equal to 2. And then I plug in a 2. I get f of 2 squared, which is 4, is equal to 4. I plug in a 4. I get that f of 16 is equal to 16. So on and so forth. I get 2 if I have f of x is equal to x, implies what? When I plug in r equals x, it implies f of 2 to the x is equal to 2 to the x. Now what does this mean for my problem? It means I'll get what? Pause for 2 minutes, figure it out. It means that I'll get infinitely many n, such that f of n is equal to n. Now, what does this mean? Well, it means that polynomial f of n minus n, call this g of n, has infinitely many zeros, which means what? It's a constant, which means g is identically equal to 0, which means what? F of n is in fact equal to n, and this is our solution. It's a pretty cool problem in my humble opinion. I like this. It has like these two big ideas, really. One is that, actually maybe 3 or 4. So maybe smaller 3 or 4 ideas. Like one big idea is this, looking at this modulo p minus 1 to get these smaller and smaller powers. And another idea is to add n plus p. If p divides n, add n plus p and you'll still get p dividing this. So that's the second idea. And from there we get to the point where we have that p divides this minus this, or r less than or equal to p minus 1 and greater than or equal to 0. And then the next thing is, okay, I probably need to prove this is 0. What do I need? I need instantly many primes. I get them. That's maybe your next idea. And then once you have this, you realize you can forget about the problem statement here. And you can just focus on finding all monic polynomials which satisfy this. And all non-constant monic polynomials which satisfy this. And from here, you're done. Like from here, it's game over. It's a walk in the park. I mean, not a walk in the park. It's just from here, you know you're done. And you need to think about it somehow. And again, use the thing that's used generally often in polynomials to finish up the problem. I like the problem. I hope you did. Let me know if you have a different solution, what parts of the problem you like or don't like in the comments below. And as always, thanks for problem solving.